Hello, my name is Novin Shahrudi, and today I'm presenting our paper Evaluation of Trajectory Distribution Predictions with Energy Score, which was accepted in ICML 2024. This work is co-authored by Michael Lepson and my PhD supervisor, Melis Gul. As in many applications of machine learning, there is inherent uncertainty in the subject of our prediction. In this work, we're interested in trajectories of agents, such as in self-driving cars, where there is uncertainty in the movement of the agents, and hence it is crucial for us to estimate the uncertainty precisely for safe and reliable planning. Let's look at the main object of our study, a trajectory. A trajectory is a spatial variable that evolves throughout time. You can look at the trajectory in terms of its past and its future. If you look at the vector corresponding to the future trajectory, it's composed of spatial variables that are s-dimensional. In our work, we're interested in two-dimensional trajectories, or bird's-eye view trajectories. Aim of a trajectory prediction is to predict the future given the past. Here we are looking at a point prediction that provides a prediction for two time steps ahead into the future. Alternatively, what we can do is to provide a distribution over the future, or predicting a distribution over the future. One way to represent that is using K trajectories. In the forecasting literature, this is typically referred to as scenarios, and in our context referred to multimodal trajectory predictions. However, in our work, we assume that each trajectory is equally probable, albeit this does not have to be. A trajectory distribution evaluation measures a distance between the predicted trajectories or distribution and the ground truth. More precisely, it's a measure of distance between the predicted and ground truth distributions, fx and fy. I is the index of n instances in the dataset. Variety loss is such a measure, which calculates the distance between the predicted trajectory and the observation. But it does so by finding the closest trajectory to the observation. Here we are looking at a number of samples depicted in black from the predicted distribution and one sample or observation from the ground truth distribution. And it calculates the distance between the closest sample from the predicted distribution, depicted in red, and the observation. Variety loss has been widely used in different probabilistic models in the literature, typically as a complementary loss, and more importantly, it has found its way as an evaluation metric, which is referred to as minimum of n or over n. Min FD and min AD are common instances of such metric. Let's get introduced with those. So for a single trajectory, the average displacement error is nothing more than a Euclidean distance between the single trajectory predicted and the observation, and then averaged out for all the time steps, as it is shown in the visualization. Final displacement error does the same thing, only that it applies for the final time step capital T. If we were to use average displacement error on multimodal trajectory predictions, we could do so by doing the same thing, but now not only averaging over the T time steps, but also over K predicted trajectories. Final displacement error on MTP would also look the same. Again, we do the averaging across all predicted trajectories, but this time for the final time step capital T. However, this strategy is not very good, as it encourages the predicted trajectories to collapse to the average of the ground truth distribution. We will see a little bit more of this later in our presentation. That is why people use minimum average displacement error, which is a common instance of minimum over n or variety loss, and it does basically the same thing. It finds the closest trajectory among all K trajectories to the observation and averages out the distance for all the time steps. Same thing goes for minimum final displacement error. It finds the closest trajectory only based on the final time step capital T. In our work, we also define L lowest of n as a more general form of minimum of n, and basically what this means is that we can take not only the closest trajectory, but L closest trajectories. For example, in this visualization, we have two trajectories closest to the observation, and basically we average out the distance across these two trajectories for all the time steps. L lowest AD when L is equal to 1 is equivalent to main AD, and when L is equal to K, it is equivalent to AD. Same goes for L lowest FD. Now, so far we've seen that variety loss as an evaluation metric is referred to as minimum of n, and the central question that we would like to answer in this work is that does it identify the optimal solution, meaning that it can recover the true probability distribution. Thiede and Brahma in their work show that in the limit of k, variety loss encourages the predicted distribution to approximately the square root of the ground truth distribution with some normalization factor c. And more generally, they empirically show that it could be of any power of the ground truth distribution, and here m, the power, is a function of k, meaning that depending on value of k, this power could be different. What this implies is that variety loss or minimum of n as a loss function would be less sharp or too sharp depending on the value of k and the dimensionality of the target distribution. And as evaluation metric, it means that it's probabilistically not calibrated, or it does not respect probabilistic calibration. And what that means or implies for the application, it means that the costs on the prevalent or extreme events are off. In our work, we study minimum of n as a scoring rule in order to answer this central question, whether minimum of n identifies the optimal prediction or not. And we propose energy score-based evaluation as an alternative, and show different ways that energy score can be employed for the evaluation of trajectory distribution predictions. Before that, let's get into definition of a proper scoring rule. Proper scoring rule is a function S that maps a probability distribution fx and an observation y to a real number. It is proper if the expected score of the predicted distribution fx is larger or equal to expected score of the ground truth distribution fy, and with the equality holding only if the ground truth distribution matches the predicted distribution matches the ground truth distribution. To understand it more intuitively, let's look at the binary classification case. You're looking here at log loss, or in case of binary classification, cross entropy. So the blue curve is the expected loss. The red cross is the true ground truth probability. And on y-axis, we can see that for any other value other than the true, what would be the expected loss? For instance, if the true probability is 0.8, if we predict anything larger or smaller this value, we can see that the expected score is going to be larger than the true probability. And what that means is that this score is strictly proper because it is minimized only at the point of the true probability. On the other hand, we can have a look at a linear loss that does not respect this property. For instance, when the value of the true prediction is true probability is 0.8, for any value larger than that, we can see that the expected loss is going to be lower than this. So it is not proper behavior. Now with this, we get to the first proposition of our paper, proposition 4.1, where we argue that the average displacement error ADE is not proper, and we can show that through a counterexample. For simplicity, we provide a proof for s equal to 1, but the principle is applicable for larger values of s as well. We take a random vector y that is normally distributed, and we can find such an example, a random vector x, such that we can see that for that example, this property is not respected. Hence, we can show through a counterexample that it is not proper, the scoring rule. For example, if we choose the x to be also normally distributed, where the mean of x is matching the mean of y, but the variance goes to 0, we can find such example where ADE for the prediction is less than the ADE for the ground truth, hence the proof is complete. Since FD is a special case of ADE, we can argue the same thing for FD, that is also improper. In the second proposition, we argue the same thing, but this time for L lowest average displacement error for any values of L smaller or equal to 2. Since the proof is rather elaborate, we refer the interested readers to the paper. But to highlight some important points, we provide the proof for X and Y, where they are distributed according to the Bernoulli distribution. And we take for a simple case where S and T are equal to 1, but the principle is applicable for larger values of S and T. Some important results is that for K equal to 2, this scoring rule is strictly proper. And for values of K equal to 1, we can see that Px, the optimal Px according to AD, is not going to match the true probability Py, and hence it is improper under such case. And for any other values of K larger or equal to 3, we can also observe the same thing, and in the limit of K we can see that the optimal Px converges to 0.5 or uniform prediction under Bernoulli distribution. Now in the last proposition of our paper, we analyze the behavior of such a scoring rule in the limit of K for a fixed L, and we can show that as long as the support of the ground truth distribution Fy is a subset of support of the predicted distribution Fx, then such a scoring rule converges to 0. Again, for interested readers, we refer them to the paper for the proof. Now let's get to energy score. Energy score is inspired by energy distance, which was introduced by Sekeli and Rizzo in the late 90s. And in the seminal work of Gneiting and Raftery, it was shown that it is a generalization of continuous rank probability score, or CRPS. It is distantly related to permutation analysis of variance, and it is discussed that it is a special case of maximum mean discrepancy in the literature. Energy score is defined in two terms. The first term is expected distance between X and Y, and the second term is intra-distance between X and its own copy X tilde. The average scoring rule for the whole data set can be calculated according to equation 2, and in the bottom we can see how the first equation could be estimated. So the first term is composed of K summons, and the second term K squared summons. Here we have written out the estimation for the norm when P is equal to 2, so Euclidean distance, and beta equal to 1. Now to better understand it intuitively, let's take an example where K is equal to 3, so we have 3 predictions depicted in blue circles in the visualization, and we have one observation depicted in white circle. So each of these terms correspond to one of these figures in the bottom. Now let's assume that the predictions are going to stay the same across multiple instances in the data set. Before that, I will also highlight that there are, as you can see, pairwise distances corresponding to the second term between all prediction sets. And we can see that there is a distance from one instance to itself, so it is shown as these self-pointing dashed lines. Now, let's get into it. Let's say for the first instance in the dataset, I equal to 1, observation overlaps with the first prediction. Here we have highlighted the corresponding distances between the first term and the second term. Next time, for I equal to 2, let's say that the observation overlaps with the second prediction, and again we have highlighted the corresponding distances between the two terms, and the third time, similarly, the observation overlaps with the third prediction. And if we pull together all these 3 instances in the dataset, we can see the similarity between the first and 2 term in terms of the distance calculation. Now let's introduce these 3 instances and the averaging of that into the equation. So as I mentioned, we assume that the predictions are staying the same for these 3 instances, so second term could be simplified as such because it's not varying across these 3 instances, so it could be simply written as such. And so here we can concretely see how the first and second term match together, except that we have this 1/2, which I will explain shortly. So before that, it is noteworthy that the energy score is minimized when the distribution of X matches the distribution of observations y across multiple instances in the data set. Now let's get into the explanation about this 1 over 2. It is best if you look at energy distance in order to understand this factor 1 over 2. So let's assume that we have multiple observations, so we have multiple samples from random variable y. Energy distance looks very similar to energy score. The first two terms are exactly the same. Now because we have multiple observations available, now we have a third term, which is interdistance between y and its own copy y tilde. What is important to note here is that the second and third term combined have the same contribution in terms of distance as opposed to the first term. So what that means is that if the distribution of y and x matches, these two terms, first term and second and third term combined, are going to cancel out each other, and energy distance will be 0 under such case. But this is a minor detail. Let's move on to how energy score could be applied to multimodal trajectory prediction evaluation. So we have a vector x, our predictions, and vector y, our observations. On the rows we have the temporal dimension, and on the columns we have the spatial dimension. The dimensionality of x is k by t by s, and dimensionality of y is 1 by t by s. As you can imagine, there are different ways that we can calculate distance between these two vectors. So one way is to entry-wise calculate it, another way is column-wise, and another way row-wise. A minor remark here is that common metrics such as mean AD are typically temporally marginalized, so correspond to this row-wise calculation. Now in the entry-wise case, the calculation of energy score would be as such. The expectation is over k, and what is most important here to focus on is that the number of terms that we have under the norm are t by s. Since we are calculating the distance between each pair of entries between x and y. If p is equal to 2, this is analogous to Frobenius distance. Now in the column-wise case, we do the similar thing. This time the expectation is over k and s. So again, to focus on the important aspect of the calculation, under the norm we have t entries of each column. Same thing goes for row-wise calculation. This time expectation is over k and t. And again, we have s terms or entries of each row under the norm. Now, to summarize, we have these three different estimations for the energy score. The first case is ES spatiotemporal, where jointly evaluates the spatial and temporal aspects, and we refer to it shortly by ES. ES temporal, or EST for short, is a case where we average or marginalize over the spatial dimension, and the third case is ES spatial, or ESS for short, where we marginalize over the temporal dimension. Now, one might ask how this could be useful. Let's take a look at a toy example where we have two forecasts A and B. Each of them produces two trajectories or two scenarios color-coded in blue and orange. And what we can see here is that A and B are spatially the same but temporally different. And when we look at the energy score, we can see that ESS gives the same score for these two different cases, exactly the same score they have, while EST is different across the two. And as expected, because ES calculates or evaluates the trajectories on both spatial and temporal aspects jointly, it is also able to detect the difference between A and B. Now we have a second toy example where we have a similar situation but in reverse, where temporally the difference between A and B is basically they have no difference, and spatially they are different. So still, one might ask how these different calculations could be useful. Imagine one would use ES to evaluate the difference between A and B, two forecasts, and a person realizes that there is a difference, but they are interested to understand where this difference comes from. And here's where calculation of EST and ESS could be insightful. So for instance, one can apply EST and ESS and see that indeed the difference is in the spatial aspects and not from the temporal aspects, and they're temporally the same or very close. Of course, in reality, it's very difficult to get exactly the same temporal or spatial difference. So this is just a toy example to demonstrate. But to put it into more realistic context, we have a corresponding parallel example. Imagine that this is a self-driving car setup where we have an agent. We are interested in predicting its trajectory, stationed at t equal to 0, and we are interested how it evolves in t equal to 1 and t equal to 2. And we can see that this is corresponding to some kind of lane-changing behavior in such context. So forecast A basically means that the agent continues in its own lane, and forecast B says that there is some lane changing happening. And we can see how these different metrics could be helpful in order to diagnose such kind of maneuvers in the context of self-driving cars. Similarly, we can come up with a parallel for self-driving car context for the second toy example, where the difference is in longitudinal distance or velocity of the trajectories predicted across forecast A and B. Alright, with this we get to the experiments and results. In the first experiment, we would like to showcase propriety empirically. So we have this simple autoregressive process which relies on the past values of the trajectory and adds some white noise to it with certain mean and standard deviation. We simulate this process for 3 time steps, and we begin all the trajectories from the value 0. So we set the mean to 1 and the standard deviation to 0.2 for the ground truth process. And for the ground truth process, we also set the parameters A and B to 0, and to generate predictions or suboptimal predictions that deviate from the ground truth, we change these parameters A and B. In total, we generate 5,000 observations, and we consider different values for K. This is how the trajectories generated from this process looks like, and it's also noteworthy that we only generate one-dimensional trajectories, meaning that the second spatial dimension is all set to 0. This is just for simplicity of analysis, and in this illustration we just superposition these trajectories for the sake of visualization. As you can see, this process is somehow analogous to trajectories with different velocities. And now we apply different evaluation metrics to this setup. On the x-axis we have the predictions with different deviations on parameter B, which corresponds to deviations of the standard deviation. And we expect a strictly proper metric to get minimized at the optimal parameter, meaning that there is no deviation equal to 0. As a reminder, L lowest FD when L is equal to 1 corresponds to mean FD, and L lowest FD when L is equal to K corresponds to FD. So here we can see that these 2 different variations of FD do not identify the optimal prediction, deviation equal to 0, and as a matter of fact, as K gets larger, they get farther from the truth. And here there is yet another observation about FD, that it encourages the trajectories to collapse, and that's because it is encouraging the trajectories to match the mean of the ground truth distribution. Here we look at the energy score, and we can see that as we increase the K, it gets closer and closer to the optimal. Still there is a bit of a deviation from the optimal, and that is due to noise, but in the limit of K we expect it to converge to the optimal. A minor note, the final ES basically corresponds to energy score applied to the final time step in our trajectory. So results from this experiment support the propositions 4.1 and 4.2 from our theoretical results of the paper. In the second experiment, we studied the effect of sample size K, and here we evaluate FD when L is equal to 1 for the case where ground truth distribution is normally distributed with mean 0 and variance 1, and across different other predictions where basically either mean doesn't match or the variance doesn't match. And one thing we can observe is that as we increase k, it converges to 0. And one takeaway is that the FD or mean FD is dependent on values of k, so it's not cross-comparable across different values of k. That is in contrast with energy score, where as we increase k, it converges to a value and gets stabilized. So in some sense we can say that it's cross-comparable across values of k, because it anyway does not depend really on values of k. Now the results from this experiment support the proposition 4.4, and with that, last but not least, we get to the real data experiment, where we apply these evaluation metrics on a real data set, ETH-UCY human trajectory data sets. We adopt the pre-trained models from an existing work, where it consists of 3 generative models and 3 sampling methods for each of these models. In total, we have 9 combination of models and sampling methods where we apply the evaluation metrics on. The goal of this experiment is to see how energy score ranks differently compared to its minimum over n, minimum of n counterpart. So this table summarizes results from this experiment. The reported values in the table are expected mean ADE, separated with a forwarded slash from energy score. The last column, AVG, is the arithmetic average over the scores of all 5 data sets. The best models are indicated with bold and second best with underline. One thing that we can observe is that energy score favors SGC and QMC on 3 out of 5 data sets. So on UNIV 01, 02, it identifies this model to be the best, whereas the minimum over n identifies SGC and NPCN on these 3 data sets to be the best. And there is a bit of a tie here on the best model on ETH dataset, and the only dataset that both metrics agree is on hotel. So they agree both on the first or the best model and the second best. So this implies that there are aspects in the SGC and QMC that minimum over n is not able to recognize, whereas energy score is able to pay attention to. And one might ask that, okay, amidst different rankings of different metrics, which one should we pay attention to? And this is a very difficult question to answer. Ultimately, we are interested in evaluation that is closest or most aligned with our downstream evaluation or downstream objective. Since we do not know that, it's a very difficult thing to do. One approach is to look at the majority vote or see what is the majority consensus among multiple metrics evaluation. Or another way that we are advocating is for metrics that are strictly proper and respect the probabilistic calibration. That means that they are matching with the probability of events happening in the data set. Now, it can still happen that a metric such as minimum over n that is not strictly proper is still something desirable because for some reason it is more aligned with our downstream objective. But this is subject to further study, and with that I will get to the conclusion. So we adopted the scoring rules framework for evaluation of trajectory distribution predictions, and we examined mean AD and mean FD as common instances of minimum of n and showed that they are improper. We also showed why AD and FD are also not a good metric by showing that it's also not proper. And finally, we proposed energy score based evaluation as an alternative, strictly proper choice, and demonstrated different marginalized variations of it that could be useful for diagnostic purposes of trajectory distribution predictions. Now with this we get to some limitations of energy score. So calculation of energy score has a computational complexity of k squared with respect to the number of trajectories. However, there are some works that provide approximations that are linearly growing with respect to the number of trajectories. Now in our work we consider k as low as 10, but there could be applications where one might be interested in values of k that is even lower than that, and this merits further investigation because energy score on low values of k could be unstable or doesn't converge as fast as one might hope for. So with this, I thank your attention, and we're looking forward to your questions if you're attending ICML. Otherwise, feel free to leave us a comment and we will address it in the comment section of YouTube. Thank you very much.